RoboCup's small-size soccer is a competition domain designed to advance robotics and AI research through friendly competition. Building a successful robot requires clever design, implementation, and integration of many hardware and software subcomponents. Motivated by an opportunity to strengthen an array of associated skills, Group 1 took part in a kicking challenge that drew inspiration from RoboCup's small-size league. In this version of the game, the robot must navigate an arena in an attempt to locate and obtain a ball before scoring into a predetermined blue or yellow goal. Whilst doing so, the robot must have mechanisms in place that allow it to avoid a number of randomly placed obstacles that scatter the arena. The robot's subsystems consisted of a drive system to provide the functionality for movement, a kicker and dribbler to provide the functionality associated with ball control, a vision system to provide a means for scene assessment, and finally, a system to provide the navigation and intelligence needed to complete the challenge.
The drive system composed of a single motor driver linked to two brushless motors with two 42mm by 19mm rubber wheels, operating as a differential drive system. This motor driver circuit was operated via the enablers from the Raspberry Pi, which when input at a high or low would control the direction of the wheels. The system chosen integrated a two-wheeled differential drive system due to its high mobility whilst also maintaining an affordable cost. To reach this final solution, certain original ideas had to be changed. Firstly, the wheels of the robot were originally a thinner rubber wheel, which wasn't reliable as it was prone to slipping during certain movements on the track. These were then changed to thicker wheels to eradicate this problem. Secondly, the motors were originally a low-torque 100 to 1 geared motors, which would suffice for reaching the speed limit set by the milestones, although not suitable when integrating as a final solution. Therefore, the 250 to 1 geared motors were utilised.
The kicker component was designed with a similar mindset to that used when designing a cap gun. This meant a high-torque motor would rotate a pinion gear, compressing the springs with the rack gear, storing potential energy ready to kick goals. The dribbler was also incorporated into the chassis, rotated by a high-speed motor at the mouth of the robot. The dribbler design was based off a two-connection point method, which proved to be extremely effective with a multi-layered balloon material surface. The chassis replicated that of the Robot Soccer League design, and a 3D printed plastic chassis proved to be an extremely versatile addition. The chassis also incorporated a modulated layer design for the above levels to house the electronics.
If you were to look at this snapshot of a RoboCup soccer field, you would likely do a pretty good job of pointing at the ball, counting how many obstacles there are, and telling roughly how far away the goal is. All our robot sees is a bunch of numbers depending on how much red, green, and blue is present. Our robot's vision system splits the image into its red, green, and blue components, then converts that to the lab color space. This gives us lightness, green, red, and blue, yellow parts of the image, which do a good job of separating the different objects from each other, similar to the way our eyes do. It checks each pixel to see what object it belongs to based on its color, and we get a series of binary masks. These are then processed and turned into polygons so that the robot can calculate how the objects are positioned relative to itself.
Hi, I'm Ryan and I worked on ensuring the robot was able to navigate the arena and ultimately score goals. The software design makes use of a state machine that allowed the system to be created and tested in blocks. In doing so, the robot has been made to play the game by jumping between 4 states. These 4 states are made up of a duplicate pair of find and seek states, one set associated with obtaining the ball and the other associated with scoring goals. The advantage of this design is that the logic associated with obtaining the ball is identical to the logic of scoring the goal. During a find state, the robot would spin on spot until the target was seen. From here, the robot would then enter a seek state and begin navigating to the target. Due to a decision to treat obstacle avoidance as a separate, high-priority case, navigation on the robot utilized an approach based on Brattenberg's vehicles. Using this method, the robot would adjust the speed of its wheels proportional to the target's location within the frame. If an obstacle was seen to obstruct the target, the wheel speeds would be overwritten by speeds that acted solely to avoid the obstacle. Once the obstacle was no longer obstructing the target, the robot could then go back to obtaining the ball or scoring the goal. Overall, the robot was found to be extremely successful. During the kicking challenge, the robot successfully avoided all obstacles and in doing so managed to score approximately 2.5 goals per minute. As a whole, the contest proved to be a very interesting and challenging domain for both research and education.